Thanks, Matt, and yeah, thank you for the invitation to come here and share some of our work with functional longevity with you guys. And Matt, you're exactly right. Our recruiters have been anxious for this one, and so we're excited to be able to release this research in need, right? And hopefully we'll continue to improve on it as time goes by and we collect more data. So today I'm going to talk a little bit about that process, right? From the start, gathering up the data, coming up with the trait definition, and then finally publishing the research EPD, as well as I want to share some of the things that we're still working on is that EPDs on the research phase and some of the things we're investigating on it as we move on, especially as we talk about modeling those traits into our selection index as well. So of course,
All right, any other questions?
From BIF, right, we've heard a lot about cow efficiency and how functional longevity and those traits related to cow ability, right, are important for beef production. And so hopefully this functional longevity tool is one more tool that we'll have on our breeders' toolbox to be able to continue to improve their cow herds. And so really this has been a priority for our Angus membership for a long time, right? And so it's been a long time coming to develop this functional longevity research EPD. And again, as I mentioned, we're excited to have this out there and breeders experimenting with it. I think we're all heard throughout the programs here at AIF this year, right? A lot of us are eager to create more tools and add tools in your toolbox to be able to select for maternal function. And I think we do have some, but I think we can gather up more data and create more traits, more tools to select for that maternal function. It was interesting on Dr. Christine Bay's presentation this morning. I think she was mentioning how many traits they have. And so it's actually an approach of there's some economically relevant traits that we want to measure and improve, but it's not really one single trait or one single EPD. It's actually a complex of many different phenotypes that we can create many different tools to be able to select for a, let's say, maternal function, right? Umbrella, let's say. And so really, of course, we have had targeting that reproduction or fertility or cow efficiency area, right? We have had the function of, the heifer pregnancy EPD for breeders to select on. Of course, heifer pregnancy is not the same as cow longevity, right? And so again, we need to continue to add more tools in there to improve cow efficiency. Another example of what we call our maternal EPDs, right, related to that cow. So we have heifer pregnancy, calving maternal, of course, the weaning weight maternal EPD, right, that's related to efficiency and costs and things like that. Maintenance requirements as we've been discussed. As you look into the end of that table, we also have EPDs for mature weight and mature height. Again, that lays into maintenance requirements and cow efficiency and the economics of that, right, that we need to watch to build a cow herd that is efficient. Of course, as we talk about fertility traits, and we've heard some of this in the presentation this morning, right, those traits are challenging because typically they are low inheritable, which makes it challenging for us from a selection perspective, not because we can't do selection, but because it takes a lot more data to get an accurate prediction, and because it takes a little bit more time to make selection progress, right? It takes a few more generations. But of course, even the low heritability traits, right? That to me, that also means that as we should start measuring those individuals yesterday, right? And continue to do so, so we can make progress in the next few generations. As we talk about specifically functional longevity, of course, we're talking about traits that are sex limited. We cannot measure on bulls. We measure the bull's daughters and how well they perform and for how long they stay in the herd and how many progeny they produce as they are present in the herd. That trait is not necessarily right. Cow fertility traits are not necessarily the same as the bull fertility traits, and so there's also areas for potential selection or improvement as we talk about bull fertility resources as well. But of course, that's not the topic for today. It's difficult to obtain the cow data, right? Complete inventory reporting, and especially if you talk about long periods of time. And of course, Angus breeders have been done a great job in collecting phenotypes from many different traits, but we know keeping that cow inventory current for many years and keeping track of records on cows for 10, 12 years or however long as they remain in the herd is challenging, right? It takes a lot of effort and dedication to be able to build that data. But that's definitely very beneficial and very valid. The other point to this is, of course, especially as we talk about the seed stock industry, and that's where we need to have a connection between the seed stock industry and commercial industry, because of the seed stock, right, we really want to turn over generations faster. And so really, we want cows that stay in the herd for a long period of time, but at the same time, at the seed stock level, we want to turn over that cow herd, right, because the next generation is an improved generation from a genetics perspective. And so the turnover of those generations is important in the seed stock industry, but of course, at the commercial level, sometimes it's desired that those cows stay in the herd and producing calves for a longer period of time, as the turnover of the generation is a little bit slower. So for us, it's important to keep that in mind, right, as we make those selection decisions, and especially as we think about what data do we need to make sure we can improve those traits at the commercial level development. Another point, right, in time right into this is, if there is an opportunity for us to capture data on those commercial cow herds, right, that could be very beneficial. And even if cows move from the seed stock herd into the commercial herds, if we're able to track and continue to report their performance, that could be very beneficial to inform a genetic evaluation like functional longevity. So this functional longevity, as I mentioned, right, has been a journey. We've been doing a lot of research to be able to put this research together. The recent research that I'm going to talk about here today really started around 2018. And I say recent research because, of course, when we had the Maternal Plus program started at Mainspring, initially they started pulling data together and trying to come up with a tool like functional longevity. But because of the challenges and the data limitations at the time, right, they couldn't come up with an evaluation that was accurate enough to publish. But of course, now that we have more data available, we're picking up that project again and being able to come up with that evaluation. So really, this research is a partnership with the University of Guelph, Purdue, and UGA to be able to start the initial model of our functional longevity, but also finally, right, being able to establish the data pipelines and the genetic evaluation pipeline to implement and run on a weekly basis. So a lot of that research involved the data exploration, and we're going to talk a little bit more about the data later on. But the trait definition itself, I think there's many different ways you could go about it. There's different models, different ways you could go about that cow genetic perspective. And so we did a lot of work to try our best, and given the data that we have, what's the best trait definition that we could come up with to make selection? Of course, the modeling approach is also a challenge. Right now, we need to do a lot of work to make sure that we have the most appropriate model, especially as we talk about these fertility traits and what are the models that will give us higher or lower heritability, and it's easier to implement for a weekly evaluation. So of course, we're interested in selecting cows that stay in the herd, right? But we don't want them just to stay there. We want them to stay there and produce calves every single year, right? For them to be effective. And so initially, we have explored two different definitions of longevity. One is what we call traditional longevity, which is we're just quantifying if they were in the herd or not. Now, of course, if they were there, you count that record. If they were not, okay, you count that they were pulled off the herd. But again, right, that could be your binary phenotype simply asking the question, is she in the herd or not? So from a data reporting perspective, that's less intensive, right? Because it's a simple question, is she there or not? But of course, that doesn't tell us much, right? We want to know if she had a calf while she was there. And so this next definition is the functional longevity. So when we say the functional longevity EPD, that functional has a very important role there, which is not only did that cow stay in the herd, but did she produce a calf, right? And so that's the whole idea behind the functional longevity, which I think you guys will all understand. It's not very complicated, right? But this is what we're trying to track and select animals. Initially on that research, within the American Angus Association, we don't have a mandatory whole herd reporting program, right? Which makes some of this research quite challenging. But we do have some individuals where we have pooling reasons, which basically tells us, okay, when that cow left the herd, she was pulled off of the herd. Why was that? Right? Because there's many different reasons why a cow leaves the herd, and some of those are directly related to fertility and maybe have a genetic connection. But some of those maybe the breeder just decided to turn generations and we sold her as a commercial. So from a stock data perspective, she's not gonna have more calves, but it's not because she's a bad cow, it's because she was sold for commercial herd, and maybe will stay there producing calves for, many more years. So it's important to be able to make that distinction when we do have those food limits. Here we have a couple papers on the initial modeling for those traits. Postdoc at Purdue that did this initial work on the modeling. So I'm going to talk about some of the results that went into there, and then we're going to talk about the evaluation that we have implemented now for the research EPD. The first part of that paper, right, our first initial thought was, okay, let's just start with the data that we have inside of that maternal plus or inventory reporting. And for the cows that we have the reason why we need the herd, maybe let's investigate if they are the same traits or if they're different traits and what's the heritability of those different reasons, right? So basically, modeling those phenotypes, you can see here, this is a table, this first part, right, is basically the functional longevity trait defined as depending on the cooling reason. So you can see natural death, structural problems, disease, fertility, and so on. And then you have the heritabilities on the next three columns of that table is basically our traditional longevity. And then we have two different models for functional longevity, depending on how we dealt with the VC data that occurs within that data set. So not going to go into too many details at this point, right? We were evaluating 2 to 15 years. So basically using the data from cows that from 2 years of age all the way to 15. And then you can see the difference heritabilities there. So as you look across those, there is some differences in the heritabilities, right? And even though for some of those traits we have other EPDs that you can use for selection, but there is some variation in those traits. Another aspect of this is, do we need to use the data from 2 years of age all the way to 15? Or can we use a subset of the data, right? Especially because after 10 years, the amount of data, the number of records that we have is relatively limited. And so if we can figure out a way to use a little bit of that truncated data, that could be helpful for prediction. Of course, as long as we don't sacrifice accuracy of those predictions. You can see that the heritability estimates are relatively similar. And of course, the bottom line there is an overall the heritability when you combine all of those together. So here's a graph. So from that initial modeling, right, trying to combine all those different reasons. So you can see each of those lines is the heritability trajectory. So the model that we're using to model this functional longevity trait is what we call a random regression model. And without going into the details of that model, right, one of the things that that model allows us to do is to plot the heritability trajectory over the years. And so because we're using data from cows from 2 years of age all the way to 15, we can estimate the heritability for each of those time points. And that gives us that nice graph of the heritability, right? So that tells us a lot of information for those traits. That also allows us to calculate the correlation between the traits across the years. As you can see here I don't have the codes for each of those lines, but it's basically following those different cooling reasons. And then you can see they more or less follow the similar pattern where the heritability increases in the beginning, reaches a peak, and then it declines at the end. I want to call your attention here to that last bit there. You can say, well, those estimates don't look very good, or something strange is going on. And really what's happening is, like I mentioned before, really after 10 years of age, but even further, 13, 14, and 15, the amount of records that we have on cows that old is very small. And so you can see that our heritability estimates are not very good. They fluctuate a lot. And so that's another indication for us that maybe we don't need to use all of that data, right? Because our heritability estimates at that point are not very good. Again, this is just a lack of data all the way up to that point. You can see here around 5 or 6 years of age, that's where the heritability of that trait is maximized. You can define it a little bit different ways, but overall it's a similar behavior. And so more recently, right, of course, for the implementation phase, and those papers have way more information than I covered here. I just brought the highlights, right, of that initial modeling of this trait. But then, of course, once we have all those details in the model, then there's one more challenge, which is can we implement that model to be able to run on a weekly basis? Random regression model is a relatively more complex model compared to some of the other ones that we use. And so of course, we need to make sure that we can feed that in within the weekly evaluation for the American Angus Association. And so that was the initiative, this part of the research that we did. Of course, we built all the modeling efforts and all the ideas that we got from that first initial research. Also, we did some work on the final trait definition. As I mentioned before, we had done, multiple trait models versus combining all those schooling reasons together. Another important point is, although we did the research with those schooling reasons for that initial couple of papers, right, the majority of the animals that we have in the database, because we don't have that mandatory inventory reporting program, majority of the animals we don't have good reasons on. And so although it's nice to separate traits like that, we need to be careful so that we don't truncate the data too much if we just use those individual evidence. And so finalizing the trait definition and the modeling, right, so that we can take the most advantage, use as much data as we can of the cows that we have information on, and also being able to run the genetic evaluation on a weekly basis. So basically, right in here, we're going to talk a little bit more about what the current research EPD looks like and what it is, right? So basically, want to select bulls, right, that will create cows, or select cows, right, that will be that will stay in the herd and produce calves every single year. That's the idea. And basically, the definition here, right, I'm trying to put it in very simple words because it can get complicated sometimes. Basically, right, on average, this will predict the number of calves sires daughters who are predicted to produce by 6 years of age, compared to sires of daughters of other sires. Now here I'm talking about APDs, right? As we use the APDs to compare animals, this would be the idea, and then I'll explain why 6 years of age, and then I also have an example of kind of how to use that APD, and that will hopefully become more clear in how that gets used in practice. Yeah, and for the data, like I mentioned, we do have some of those cows inside the maternal plus program and some inside of our inventory program. And so we're using that data, and where we can, we use those schooling reasons to edit the data and to make sure the data is good inside the evaluation. But we're also taking advantage of some of our data, because of course, if we have a Cantonese record or if we have a birth weight record on a calf, well, that calf has to be born out of a cow, right? And so we can track that information and use that information to give credit to those cows that are reporting those calves. So this is our functional longevity research EPD. So we released this research EPD back in October of last year, and we've already done one update to that EPD on February 15 of this year. Again, these updates, right, especially with the enrollment periods for inventory reporting, those are typically the periods we get a lot more data for this functional longevity trait, and so it's interesting to do updates on those EPDs on those periods of times as we accumulate more data. Of course, eventually, once we're done through that research phase, right, hopefully we'll publish that EPD in a production mode, as we call it, and then of course, will be updated every week. So I wanted to give you guys a little bit more detail on what the data looks like and how we're modeling this data in functional longevity. So we'll go into a little bit more details on how the data set looks like. So as we're looking into the paper right inside of inventory reporting or maternal plus, and I'm pretty sure I stole this slide from Esther, so thank you, Esther. Just kind of trying to break it down, right? And as we talk about, this is not valid only for functional longevity evaluation, but just as we look into the cow data as a whole, and this is why inventory reporting is so important, is because it gives us this kind of insight, right? So this pie chart breaks down some of the reasons why the cows leave the herd. And I think the more complete data we get, the more insight we'll have in some of those reasons. And as you guys can see, some of those reasons we can say, well, there's some of those things that we can address using genetics and maybe creating tools or using the current tools for breeders to select and hopefully address those, right? So talking about the data, right? So this functional longevity research, it does include data from the American Angus Association and the Canadian Angus Association. So taking advantage of and using the Canadian data as well to increase the accuracy of those predictions. Right now, we have just under 2 million cows in that genetic evaluation. That gives us about 8.3 million records. we're using, and you guys see the example, we're using data from cows that are from 2 years of age to 10 years of age. So each cow can have 9 records in the evaluation, so that's why we have 2 million cows, but over 8 million records. So each cow can have multiple records. We're using all the genotypes available, and then of course, the pedigrees as well. As we look across the inventory reporting and maternal plus, I thought this would be an interesting stats to show. And as I mentioned, right, maternal plus program has been around in the Angus breed for quite a while, but the inventory reporting is a little bit more recent. And of course, it's not a mandatory program, so you can see the difference in the amount of records that we're using. So on the first row there, you can see inventory reporting for maternal plus. So cows out of those programs, basically around 275,000 cows for roughly 1.2 million records. And then outside of those programs, which is where we're taking advantage of pooling reasons, of the cabin records and the birth weight records and so on, right? 1.7 million cows and around 7.1 million records. So as you can see, the distribution, we're still relying on a lot of data that's outside of our inventory reporting program, but hopefully as the program progresses, right, and hopefully people get interested in functional longevity and looking into more closely as those maternal tools, we'll get more people involved in inventory reporting. And so I think our functional longevity evaluation will be set up to take advantage of that data as it comes in. Also, I don't want to, I'm saying that there's not a lot of data in there, that's still 1.2 million records, right? So I don't want to downplay the amount of records that we have in that evaluation, just highlighting the differences between the two. But of course, we have quite a bit of data in that evaluation. Here's an example, and for, of course, this is a generic example of what the data set looks like. Sometimes on fertility-related traits, right, one option to use to evaluate those phenotypes is you can use it as a binary outcome. So did she have a calf or did she not? So that's the 0-1 binary phenotype. Sometimes that creates quite a bit of challenges, right, from a modeling perspective. So the way we model the functional longevity is, as you can see here, is the number of calves. So the phenotype of cow is the number of calves that she had. And so for each year, right, did she have a calf or not? So that's +1. So for example, if you look at my cow 1 over there, well, I'm getting my head ahead of myself on the slides. So for each of those cows, right, they can have multiple records. And so which cows are included in that data file right now is, again, inside or outside of our inventory report data. I think for our case, you can see there's as much data outside of those programs, so you need to take advantage of that. And basically those cows, they must have a 2-year-olds, and so to be included in the evaluation. And then we're using 8 cows from ages all the way from 2 to 10 years of age. So each cow can have 9 records in the evaluation. So 9 tracking events, if you will. Of course, those tracking events could be successes or failure, right? That's where we create the variability in the data. And then the phenotype is really the number of calves. So for each year, she had a calf or not, and we add +1. And we're modeling that inside of the random regression model. So it's random regression model, but we're not using the binary phenotype. We're counting the number of calves as the year go by. And here's where I got lost in my slides because I had the table in the previous one. But here's, if we go through more details, right, I tried to create some examples to show, okay, how does that data actually look like? And here you can see my cow 1, she's 10 years of age, so all those records are included in there from age 2 all the way to 10. And then of course she has 9 records in the evaluation, and basically she has 9 calves, right? So for every single year, she was a success. So that's a complete phenotype, right? We have all the data, and she has had a calf every single year. Now, as we look at cow 2 here, she has 3 years of age, right? Only 2 records in the evaluation, but she only had 1 calf. So if you look into the middle column there, which is the actual phenotype, right? She has 2 records, but only 1 success. And then here's some more examples. You can see cow 3, 7 years of age, 6 records, only 4 calves. So you can see that the way that gets modeled, right, we repeat. So basically a cow has more records than she does calves. And so that's really what creates, and again, this is just a generic example to hopefully give you guys some insight on how to model that. But basically that's how the variation is created inside the evaluation, because the cows can have the same number of records in the evaluation, but they would have a different number of calves at the end of the day. That's what creates the variability. As we look into distributions and some summary statistics around the data that I thought would be helpful to show you guys. As you can see, this table describes average age. You can see medium and maximum, of course, 2 years of age all the way to 10. On average, around 6 years for the cows in the data set. For records, of course, the average number of records is 5, and then going from 1 to 9. So some cows have just 1 record. If you think of a young cow, right, 2 years of age, she can only have 1 record in the evaluation. Of course, as she gets older and has more cavity events, we can add more data to that particular cow. And then this one I think is interesting. The number of calves, you can see about 3.4. So there is a little bit of a difference, right, from the number of records to the number of calves, which means, of course, there are some cows, right, they don't have perfect records. So they're missing some calves. And of course, that's what generates differences in the variability in the data. Here's another graph showing kind of the distribution, and this will give you an idea what's the age of the cows and distribution over the distribution of the number of cows for the age. So you can see at age 2, we have 1.9 million individuals in this bar. It's because at age 2, right, all the animals, all the cows in the evaluation are required to have a record at 2 years of age. So I have all the animals. As you go down 3, 4, 5, all the way to 10, you can see the number of cows decrease, which makes sense, right? As those cows get older and older, we lose some of those cows get sold, some of them die, and then we lose some of those records over there. So the number of cows that actually make all the way to age 10 is relatively small inside of the data. Going back to our previous discussion of using data from, to 13, 14, 15 years, yes, we could even use that data, but as you can see, the number of cows decrease a lot as the age goes by. This is another table that I thought would be interesting to share. I know it's a little bit complicated, so hopefully I can do a decent job of explaining what the data we have here. So here, basically, we have on the x-axis, the first column, we have the age of the cows. So basically from ages 2 through 10, you can see the number of cows, which is what represented in the previous bar chart. And then on the rows there, you can see the number of calves. So I'm just trying to represent, okay, of the cows that are 2 years old, how many calves they have. And so you can see, as I mentioned before, all the cows at 2 years of age, they have to have a calf to enter the evaluation. So 100% of those have 1, right? And as you go on, so for example, if you take the cows that are 3 years of age, I'm getting my rows correctly, right? 73% of those have 2 calves, and then 27% have 1. I'm not gonna read all of those rows, but for example, if we look at age 6 and go back to 2 calves or 3 calves, right? There are still some cows that are still in the herd, they're still there, but they have 2 or 3 calves on them. And so I think, especially as we talk about inventory reporting data, it's interesting for us to dig through that data and understand, okay, why those cows are there? We just continue to give them chances, right? And maybe should they be there? I think that's also some kind of insights that this kind of data could provide us, and I think it's interesting to try to dig through. As you look at the diagonal of that line, right? Of course, we would like to have 100% in the diagonal line, which means, as she has 2 years and 1 calf, 3 years and 2 calves, and so on. But of course, that's probably not realistic. But I think this kind of representation of the data could be interesting to get more insights on what's going on with the population. So now we're going to talk a little bit more about heritability and genetic correlations. Again, I showed you heritability graphs for that initial research and splitting by traits according to different pooling reasons. But here's heritabilities and genetic correlations as we talk about this kind of final version of that model. So here's that same graph from that random regression model of the heritability trajectory across the years. And you can see it follows a very similar shape as the ones that we have represented in that initial research. What I want to point out here is you can see the heritability peak or maximized around age 6 at around 10%. So again, similar to what we saw before, it kind of representing the same behavior. At age 2 here, I will point out this looks close to 0, right? And it's kind of weird. But that reason is because as we are As we make a requirement for the cows to have a calf to enter in the evaluation, that also means all the cows in the evaluation have a record of one at age 2. And so that creates some challenges for us, right? Especially with the data editing and how to model that. But basically that means that age 2, there's no variation. And so we rely on those older years, right, to be able to estimate the heritability. And really, we can't get a good prediction of heritability at age 2. As we look into correlations, again, as I mentioned, one of the other functions of the random regression model is that we can correlate the predictions or the genetic correlations across the ages. And so here I'm showing from ages 3 to 10. Again, age 2 is a little bit tricky, right? As there's no variability there. But as you look across, you can see the diagonals here would be the heritability we just saw on the graph. But as you look across, you see the correlations, the genetic correlations between the ages. I know that table has a lot of numbers, so I'm just highlighting the age 6 here. And you can see in age 6, as you look across the right-hand side, the correlation between age 6 and the subsequent ages are very, very high. And if you go across the other rows, you can also see the same behavior. And as you look across that table, right, that means if the genetic correlation between age 6, 7, 8, and 9 are very, very high, that's pretty much the same trait. So we can predict the APD at age 6 or age 7 and age 10, and the ranking of the individuals for those different traits would be essentially the same. And so basically that tells us some information about, okay, where do we need to predict these EPDs? Because as we talk about this random regression model, right, it has a lot of advantages and allows us to do a lot of interesting things. But then now we could essentially predict an EPD at age 3, 4, 5, and so on, right, all the way to 10. And of course, that's very confusing, right? That's one EPD sometimes is confusing enough to select on, especially as we have many, many traits. And so we need to decide which of those would be the most appropriate one to actually predict the EPD at. And basically, as we look across this functional objective EPD, right, to us, it made a lot of sense to predict the EPDs at 6 years of age. And one of the reasons for that is that's where our heritability is maximized. So we want to take advantage of the highest heritability. And as you saw on the trajectory graph, 86 is where the heritability is maximized. As you look across the genetic correlation with other years, 6, the genetic correlations are very high, so that's another indicator that we can predict at age 6. Also, if you think about a production perspective, right, I think we predict that at age 6, it makes sense from a production standpoint as well. I think it's important to point out that, especially with this random regression model, which is very similar to what others use to analyze these kind of traits, right? We're still taking advantage of all the data that's available. So all the data from maybe 7 to 10 is still in the evaluation. It is, of course, contributing to the accuracy of those EPDs, but we're just predicting the trait diagnosis. Now here, practical application, hope to give you guys some more visibility of what the EPD looks like and what would be a use case and how we would use this functional objective research EPD. So hopefully, going through the steps of the initial research that we did, the actual implementation, heritabilities and genetic correlations, and also now a little bit of how we use this. So here's a distribution. As you look across that distribution of this research EPD, you can see how many animals we have in there. I did some filtering to create the table. Basically, on average, we have around 1, and then a mean max of 0.39 to 1.48. Of course, there's base adjustments here as we prepare those EPDs to be published. Accuracy on average of 0.21 accuracy. Of course, relatively lower accuracy compared to other traits, even though this is not a validation accuracy, so not a prediction accuracy. But with a heritability of 0.01, you expect the accuracies to be overall a little bit smaller. Even though, right, of course, you would have bulls with a lot of daughters with a lot of progeny in the evaluation. So you can see the accuracy ranges from basically 0 to 1, as you have some individuals with a lot of daughters in the evaluation. You can look around and see on that table, and of course, as we're talking about ranking animals, you can see the difference from the top and to the bottom, right? And the difference is about one calf, which I think is not an insignificant difference, right? I think if we can select and make improvement over time, I think that could be a very significant. Of course, we know that it's a relatively new trait, heritability is small, the spread of the EPD is relatively low, but I think there's still enough variation there to be able to make some genetic gain. Here's a graph of the distribution of that EPD. You can see it's a nice normal distribution as you would expect. Again, I'm pointing the red line in the middle there, that's where the average of that EPD is. I think this is, of course, not a big surprise, right? But it's just to show some nice bell-shaped curve distribution of those EPDs. I'm showing here the average of standard deviation. Again, standard deviation is relatively small, especially in the longer term. Here's another point, and as we're exploring the research EPD, right, we start looking at the numbers, how do they look like, and what does that mean from a selection perspective. This is plotting the genetic trend as we look at that functional longevity research EPD. And you can see I put the numbers here from the left-hand side to the right-hand side, 0.925 to 1.07. So basically, when you look at the graph, you may see like there's a slope there, but really it's relatively flat genetic trend, right? And if you put it into context, that's the difference of 0.12 caps from 1990 to 2022. So that's not a very big difference, right? And of course it makes sense because there hasn't been direct genetic selection for that trait as the EPD was not available to now. So hopefully we can change this genetic trend going forward. And here I'm just representing the genetic standard deviation because sometimes it's hard to look at absolute values, which you can see is a fraction of the genetic standard deviation over time. As we look across this functional longevity EPD and think about how do we use it and what does it mean, as the unit of the trait is the number of calves, right, at 6 years of at the EPD, that's the same unit. So the unit of this EPD is the number of calves at 6 years of age. And basically here I have a very simple example, and this is a generic example as well. You can see that I made it very easy for myself as bull A has a 1.5 functional longevity EPD and bull B has a 0.5. So that gives me a difference of 1. Very easy and simple for me to get through the presentation. So basically, if we put it into context, right, of interpreting EPDs as we do for wean weights and so on for the other traits, right, basically looking into this example, the difference between those two bulls is a 1, which means sire A's daughters are expected to produce 1 more calf by age 6 compared to bull B's daughters. And really, as we're thinking about this EPD to rank animals and make selection decisions, right, this is how we interpret. Of course, as we look into the actual numbers, gets more complex, but this is the overall idea. And of course, here, if you back up a little bit and think about what's the breeding objective, what are we trying to do? If we're goal is to increase the number of calves the cow is producing and even the herd, a higher functional longevity EPD would be beneficial, right? That's the direction we want to go. Now, we did do a little bit of validation in front, and I don't do validation on necessarily the statistical forward prediction type of validation. We did some of that as well, but here I'm showing a little bit of looking into the data kind of retrospectively type of validation. So basically what we did is, okay, if this functional longevity EPD is predicting animals with higher genetic merits to, produce daughters that will need more calves in the herd, we would expect that if we separate those individuals, they would have on average more calves, right? And so what we tried to do is we kind of truncated it in different ways, but tried to select a group of animals that would be representative. And so we took here sires born before 2010, and that had at least 10 daughters with 10 years of reference. Now that's a very specific criteria, but why that's important? Because if we compare bulls that are young, it's going to be very hard for us to look at phenotypes, right? Because their daughters didn't have time to produce calves in the herd. So it's very hard for us to benchmark. And I should give a shout out to Pedro here that did all the work. So I got to present, but I had a lot of help going throughout this research project for sure. And so this is what we tried to do. So as we did that, what we did was once we had that set of bulls, we tried to separate them in percentiles from the functional longevity evaluation. So here in this first part of the table, you can see the top 1% versus the bottom 99th percentile. And of course, here the number of sires is relatively small, so we have to take this result with a grain of salt. But as you can see, right, the average number of calves reported out of daughters of those bulls, right, for the top 1% was 4.6, and for the bottom 99 percentile, right, 3.2. So a difference of 1.4. I think that's a significant difference, right? If you rank the animals based on functional longevity, that's what's showing us that those bulls that are higher rated for functional longevity are expected to produce more calves. And then basically we broke down the different percentile levels, right? This is the 5th percentile. Of course, here we have a little bit more animals, right? So that gives us a little bit more confidence. And you can see the difference as well. And then the top 10 percentile, and then the top 20th percentile. Of course, as we get closer and closer to breed average, right, it's hard to pull those differences apart. And so really, the contrast is more apparent when you pull the extremes in the population. But you can see all the way even to the 20th percentile, when you separate those individuals, we still got quite a bit of difference in the number of calves that has reported. Again, this is a data set that we had to do subsetting, right, to make sure that we had a fair comparison between those two groups of individuals. But I think it gives us a good example, right, to show that this EPD is appropriately ranking the animals for functional longevity. As we talk about these numerical traits, right, on the risk of repeating myself here, we know those traits are low heritability, right? And I would love to have a 0.3 heritability for our functional longevity repeat, but of course, that's just not reality. And so we have to understand that, and our functional longevity predicted at 6 years of age, right, has a heritability of 0.09. But I think that tells us that that's even more important to collect data and start making selection decisions, right? I think we should not be discouraged by the size of the that's just a part of the population that tells us that we need to make even selection decisions that are based on data and based on PPDs specifically, right? At the end of the day, what this low heritability tells us is that our ability to predict the genetic variant of individuals by looking at them is very small. So if you think you can select the best cows genetically by just looking at them, that heritability tells me that that ability is very limited. So it's even more important to use the EPDs to select individuals from other traits. Right, so as we look at the heritability that low, that there's a lot of influence from the environment on those phenotypes that we observe. And especially now, right, that we do have the functional longevity EPD, right, it's very important that we use and model that inside of our selection indexes and take the EPDs into account when we make our mating decision selection decisions. So moving on a little bit from the presentation, right, moving on to that kind of last part, talking about what are some of the next steps. We're still working on this research EPD, and I think even once we publish this EPD, I don't think we solve the maternal question, right? I think we still need to continue to work, especially as we get more data inside of inventory reporting. So we'll continue to create tools and improve on the ones that we already have. But some of the next steps is that research EPD is going to stay in that research EPD mode for several months as we gather more data and do some more investigation, as well as I think collecting feedback from our members is very beneficial, like making sure that that EPD makes sense and is easy to use and is useful for them. One of the things that we are very interested in, unfortunately, I don't have results to show you guys today, is the genetic correlation between functional longevity and some of our other traits, especially as we talk about selecting for growth, carcass traits, and environmental adaptability, maternal function. One of the first things that we need to understand is how those things are correlated. And so this is the next one on our to-do list. That also ties into modeling functional longevity inside of our selection index, specifically $M. So we need to understand those correlations to establish the relationships between functional longevity and the other traits, as well as understand the economic impact that functional longevity has, and of course, take that into account on our indexes. One other thing that we're interested in looking at is, of course, we have quite a bit of data from inventory reporting versus non-inventory reporting. And we're really interested in to do some more investigation, make sure that, you know, can we maybe even ask the question, is that the same trait even, right? Because we know those data sets could be a little bit different. And so from a research perspective, we'll be interested in that and poking that data around, see if we can find something interesting in there. As we talk about these research projects, right, I just wanted to put a plug here for our summer interns. So, Suleika Trajano and Kui Wen, they just joined us in the past couple of weeks in the office. And they will be working, among other things, right, on some of the genetic correlations that I just talked about. So hopefully through the summer, right, we'll be able to have some results on those genetic correlations. I think that will be a very, very interesting project for them to work on. I hope that this got across as I talk about functional longevity, right? Complete data reporting is vital for us to improve. And of course, I'm talking about functional longevity, PD, but as we think about maternal traits, and I don't think this is just an Angus idea, right? As we talk about maternal function across genetic evaluations for different species, even complete data reporting is vital. And of course, it's important for us to know when the cow had a calf. But I would argue that in some cases, it's even more important to know when she didn't have a calf, and more importantly, even why didn't she have a calf, right? And so I think being able to make that distinction help us understand the data and the population a lot better. And that gives us opportunities to create a lot more tools and develop more EPDs to select for maternal function. For the Angus breeders in the room, right, we have our inventory reporting, and I have those enrollment dates there. I hope I didn't get them right, Devin and Esther. I hope I got them right. But I think that's a great, that's, if you want to do some action, right, of course, we have the research for you to look at out now, but participating in inventory reporting would be very beneficial as we talk about those traits. I know this presentation had a lot of information, right? And we have a lot of resources out there as well. So I encourage, of course, doesn't matter if you're an Angus member or for some other breeder, if you're just interested in what we need for functional longevity and how we model the trait. We have a lot of other resources that we put out there. If you're interested, I invite you to go take a look. And we did a functional longevity research webinar, which has some of the information that I shared here. So if you want to go back and revisit some of that information, that's available out there as well. With that, I again appreciate the invitation and appreciate you guys sticking with me here this afternoon and listen about functional longevity. And I'm happy to take any questions if there's any. Thank you.